Okay. It's going. 1 second. I was waiting too much time.
Okay. So.
Okay, we are live.
Okay, we are live. Great. So I think we can start, correct?
Yes, we can start.
Okay. The floor is mine. It's really a pleasure to introduce Chris. So we will introduce you together. Me and Stefano, I start and then Stefano go on because he's physicist, so you know the same discipline. So it's really a pleasure to have you here. So
thank you.
Chris is a full professor and director of data science at the Center for Complexity at the National University of Mexico. And I didn't know, but this is the oldest university in the Americas. So all the America, North and Central and South, correct? So he graduated in physics at Queen College, correct? Oxford, so comes from Oxford. And he got a PhD in theoretical physicist from the University of Maryland. He worked in many different places, University of Glasgow, Imperial College, University of Utrecht, actually got a lot of prize. He was a Marie Curie Fellowship at the Dublin Institute for Advanced Studies, so long career. And he also founded 2 companies, correct? Are you the CEO?
Yes, I am the Director General of the company.
Okay, so you have a lot of responsibility as well. So, and the 2 companies, if I understood well, works on artificial intelligence, research to business and industry with emphasis on healthcare. So, very comprehensive. Stefano, you want to say something else?
So just to say that Chris worked in very abstract theoretical physics, if you say, particle physics. He worked with Gerd Toft, who's the winner of a Nobel Prize for electroweak symmetries, I think. So I'm not even an expert in these things, but today he will talk about very different subject that has nothing to do with physics, as we were discussing before, something that in which the mindset of a physicist can be useful. And it is about the conductome, so how people behave. And without further ado, I will leave the floor to Chris to tell us about all this.
Thank you. So, yeah, it's a real pleasure. Good morning from Mexico. So I guess the thing is that if there's questions or anything like that, you guys are the only ones who can actually interrupt me and say, hey, Chris, what about this? As opposed to the people watching on YouTube, right? Where I guess they put in the comments. So the one thing that's never left me is my appreciation as a physicist of being interrupted, because the thing is that, if people don't pick at you, then the point would be is that you're either saying something not interesting or you're not going to learn anything new. So please feel free to pick at me at any point. So I'm going to talk today about this concept, the conductome. I talked a little bit, I talked somewhat about it at Lake Como. So I'll follow up on that and try and get across to some extent what I think are truly enormous challenges for science in general and for societies in general, and how science can help societies function better. And one of the main things I'll concentrate on there is just the concept of true multifactoriality that is an inherent characteristic of complex systems, right? So the thing is that you could first start off, well, okay, why is conduct important? Basically, conduct is the chief means of interaction, let's call it, between any living organism and its environment, right? But another way of thinking of it in more concrete terms is the concept of just decision making, right? And basically every major problem that exists for humanity is a consequence of our decisions and the adverse consequences of those decisions. So it doesn't matter whether it's climate change, doesn't matter whether it's healthcare, epidemics such as COVID itself, or obesity, or something like that. They're really all at heart a consequence of our decision making. Now, the thing is that in some sense, where to think of where the physicist's viewpoint could start to come in. One thing I always like to say, I don't care whether it's a business situation or a scientific situation, or just any situation in your own life. There's no concept of a decision without a prediction behind it, right? So sometimes what I like to sometimes pose is the idea that any living organism is just a big bunch of prediction algorithms, right? The prediction models. Nobody flips a coin, although it might seem like it sometime, about taking a decision, right? There is basically just a prediction model that basically tries to ascertain what are the potential consequences, good or bad, of a decision and a consequent action. And those decisions, those prediction models rather, have to be fed by data, right? And it's another talk to basically go into how we've gone from prediction models that are generated by data that's analog, in other words, what we see, what we hear, et cetera, to basically a digital world where 99.99999% of all data on the planet is now in digital form, and unfortunately we don't speak database, right? Now, so the thing is that that's just to pose the question of, or the notion that conduct is supremely important in our lives, right? So the thing is that what's an omic perspective, right? The omic perspective, in some sense, is obviously everyone's familiar with genome, proteome, transcriptome, et cetera, the bioinformatic microscopic omes. But what it has behind it is basically the idea of related to the totality of something, right? And the thing is that this is nothing new in some sense to a physicist or probably a chemist, in the sense of what's the periodic table other than, let's call it an atomome. It's the set of all possible configurations of atoms, right? And their properties, relations between them, et cetera. Now, the thing is that these ohms, in some sense, can look at things from two different perspectives, right? It's basically one of the most fundamental ones, and once again, from the point of view of physicist, it's the idea of what are the structures, what are the what we would call them sometimes, what are the effective degrees of freedom associated with phenomena at a particular scale. And we think of genome, epigenome, proteome, etc., like basically systems biology concepts, like supposed to span a lot of different scales, but in one sense they really don't, right? Not when you go from you're talking about scales that go from very microscopic, like an atomome, let's call it, to basically extremely large scales, where we're talking about disciplines such as sociology, economics as being important. So the thing is that the idea is at least try and take a bigger, a wider view angle of things when you're talking about an ohm, right? And in that sense, one of the things that's driven the bioinformatics revolution in that sense is the idea that we could just get lots and lots and lots and lots of data, right? But back to a physicist's in this sense, I would say, at least on my own part, although it's not true much of the time, but let me talk about humbleness in the sense of one of the biggest challenges is how you go from phenomena one scale to another scale. So in other words, it's one thing to say, okay, well, how do molecules come from atoms? And in one sense, it's still from a first principles point of view, it's a huge challenge. Well, even far more so when you say, okay, from a particular genome, how do we get to diseases? There are some where there's a particular polymorphism where it's fairly clear how that one particular polymorphism induces a particular disease. But when we talk about diabetes, or when we talk about the majority of diseases, the relationship between what's happening at the microscopic level and what's happening at the macro level is just, forget it. We have very little idea, right? So there's this progression, that we can call it, where going from one scale to another is the most difficult thing, essentially, in science. But what this omic perspective has going for it is at least it's trying to look at things once again using this wide angle lens rather than just looking at one particular phenomena at one particular scale, right? Okay, so the thing is that how do we represent ohms? I would say there's two. This in some sense comes from the Lake Como meeting with Plamen, etc., emphasizing the notion of networks as being a very important. Yeah, go ahead.
You're not seeing the slides. I don't know if you're sharing the slides.
Oh, that's weird. So let me escape. Yeah, I was showing them. I have no idea why it stopped sharing there, Stefano. Can you see it again?
Yes, now it's fine.
Yeah, it's weird. Okay. So basically, what I'll try to propose is, there's two main, let's call them, representations, both mathematical and from a visualization point of view, of ohmic concepts, right? One is, basically you have a bunch of entities, structures. Here it's like the idea of transcripts or metabolites. And the thing is that you can put them all together and you go, well, how is one related to the other? And that leads us to, say, let's call it a network point of view. And related to that, let's call it ecological communities. The reason I say that is, like, a good friend of mine, Pablo Marquet, who's a very well-known ecologist, almost began to convince me that ecological concepts were actually at the heart of everything, more than even physics concepts. And there's a certain truth to that, right? So in physics, we talk about interactions between physical structures. In ecology, we talk about interactions between organisms, right? But obviously, this network point of view is kind of equal to both. Depends on what we represent as the nodes and the links. Now, the thing is that the second concept is the concept of an ecological niche, which I think is incredibly important. A lot of what I do in disease ecology is to say, well, what's the niche of dengue? Or what's the ecological niche of, you could say even COVID, right? And the idea there usually has been that, okay, well, an ecological niche is to do with the weather, it's to do with what other animals are around, etc., etc. But the thing is that if we look at it from a broader perspective of saying, okay, what I want to do is just say, what's the probability of this thing given these other things, right? So in other words, what's the probability of basically finding a pathogen in a particular place as a function of what's in that place, right? Well, obviously the concept of a conditional probability like that, if we're thinking as a mathematical representation of a niche, what's the probability of diabetes? What's the probability of somebody buying your product or something like that, right? So let's call it the purchases of a particular product have a niche. Diabetics, there's a niche that's in some sense related to the presence or absence of diabetes, obesity, or whatever it would be, right? So in that sense, if you think of a network point of view, one thing that relates the two different ways of looking at things, either a community or a niche, is essentially the concept of like a Bayesian network, right? Unfortunately, Bayesian networks are extremely difficult to work with from the point of view of trying to match them to the data, right? You know, he's just one particular example of trying to relate cause and effect. But let's call it non-alcoholic fatty liver disease versus metabolic syndrome, and how you can go in both directions potentially on what causes what, right? And once again, this is one of the huge challenges, right? You know, what does hypertriglyceridemia come first? Hypercholesterolemia, obesity, etc., right? How one relates to the other, and obviously, trying to have timestamp data that would tell you that somebody giving you a blood sample every day of their lives is a non-starter, right? So we have huge challenges at trying to infer what causality is when we're talking about complex systems. But at the end of the day, the one thing I'll be focusing on, and this is going to be what it is the conductome, is that we'll take this class, to just be a particular behavior, right? So in other words, hey, what's the probability that somebody doesn't exercise, or exercises only less than 2.5 hours a week, or etc., right? And once again, one of the characteristics of complex systems is that the number of variables we can put into our specification of the class that interests us can be enormously multi-factorial, right? So in other words, you know, you could say, what's the probability of being obese? Well, what's the probability of obese, and you're this gender, and you're this age, etc., right? To be able to distinguish different niches, let's call them, for different categories, let's call them, of say people. So as an example, you know, we could say, what is the obesity niche? You know, what does the probability to be obese depend on? And we think of that as an effect, right? So what are the causes? Well, the thing is that some potential causes, and this is, you know, just one of the data sets that, you know, I've explained to Kate and to Stefano. We have literally thousands of people in our studies, and literally thousands of variables of those thousands of people, right? And this is just one subset of the data. So you can say, well, does it depend on your age? Well, you know, for the present, you know, data set that I'm going to be showing here, you can look at it as a function of age. What does the proportion of obese people look like? So as a function, it's basically almost always a kind of a parabola, right? Just how symmetric it is it depends on the actual data set you're looking at, etc., right?
Just a short
yeah,
question.
Ronnie.
IMC is BMI, or it's
yes. Sorry, yeah. That's not translating every last thing from Spanish into English. Yeah,
okay.
It's BMI, exactly.
And the graph you just showed, it looks like it's getting into a kind of a plateau, and at later age it's dropping.
That's exactly what happens. Yeah, I mean, basically, you know, well, you know, if there's time at the end, Ronnie, or if there's interest, I can show more data sets in the following sense. One of the big national health and nutrition surveys here in Mexico. So this is like 1,000 people. So if we look at that data, it's like 20, 30,000 people. And the point would be is that you get a nice smoothing out, in the sense of it really is a symmetric parabola. If you look at the famous NHANES studies in the US, then it's more asymmetric, right? You know, so in other words, it's parabolic, but the way how it comes down on the older side is different, right? And part of that is like the difference between what we've got here is a transverse population, right? But the thing is that to what extent can you also thinking of it as representing a longitudinal aspect, in the sense of, hey, how do people get fatter and fatter and fatter in a population as a function of age? Obviously, that requires assumptions about, hey, the world isn't changing that much from one year to another, et cetera, right? But generically, what happens, and from an epidemiological point of view, that's very important, is that the highest rate of BMI increase is as a young adult. So the thing is that this data is, because it's university workers and academics, etc. We're going from like 18 to over 80. But the thing is, no matter what data set you look at, basically, you could probably argue that 60-70% or more of population level BMI increase occurs between 20 and 30, right? So those are crucial years. It levels off at about 50 to 60, and then it starts to come down again, and that's because older people just eat less. Obviously, your metabolism slows down. There's many things there, right? I mean, that'd be a whole different talk in itself, just the geriatric aspects of that and the aging aspects. Educational status, basically this is secondary school, primary, so basically high school, bachelor's degree, master's, doctorate. The one, if I ever have to say there's a magic bullet to obesity and health, it'd be education, right? But it basically means nothing, right? So, so I sometimes joke with people, I'll just give you a piece of paper that says Dr. So-and-so, and we'll see if the obesity rate goes down. Well, that's not the case. But, one of the main basically goals of our studies is to find out what is behind fundamental things like socioeconomic status, but educational status is even more important. What is it in people's behavior that differs as a function of education, right? So in other words, it's not a causal driver in and of itself, but what are the causal drivers behind that? I mean, so in other words, in the UNAM, it's like the obesity rate is 13% among academics, and it's 40% among workers, right? So if you could take the Mexican population and turn it from 40%, which is what it is, approximately in terms of obesity rate, into 13%, it's like, it'd be an enormous, enormously important goal, right? So gender, doesn't make much difference. What about your genes? Well, in the first study we did, we took about 300, this is, quite some years ago now, 2014. We were working with the National Genomics Institute, just took about 300 polymorphisms that have been previously associated with diabetes, obesity, et cetera, and just see, okay, well, how do those paint in terms of predictability? So this is kind of a concept that we'll use frequently. It's the idea of, hey, given that I'm looking at everything, what's the conditional probability of this given this? Well, rather than looking at it from a multifactorial point of view, you can just look at it variable by variable, right? Okay, so in other words, hey, 21% of my population are obese, basically there. And what's the population of somebody who has this property? You're male, you're female, you're 20 to 30 versus 30 to 40. You've got high school, maximum educational status. What's the probability that you're obese? So there are some SNPs there where they, in some sense, look like, oh, yeah, there is a certain propensity that gives them statistical significance beyond, just random chance. That's what this epsilon is here. It just represents the number of standard deviations that this probability is from this probability is a binomial test. But one of the things you'll always find, you always use as an argument about genes, in terms of polymorphisms at least, is not particularly useful, is the coverage, right? So in other words, out of the 567 people that we were doing the genetic testing on, only 10 had this gene that, or polymorphism that was actually, in some sense significant, right? So when you're trying to explain that 40% of your population are obese, then, having a particular polymorphism that links to obesity through, let's call them physiological links, is not particularly useful as an explainer of the overall problem, right? So one of the ones I do like is this one. What's the probability of being obese as a function of your height, right? So the thing is that you see the absolutely enormous difference between short people, and tall people, right? And that's one of my favorite ones that I've always wanted to try and devise some really cool experimental protocol to delve into it in the following sense, right? What I always tell people, there's no such thing as a Big Mac for short people and a Big Mac for tall people. But if you think of it, once again, thinking of my physicist had, well, how many cells does somebody who's 1.8 meters tall versus somebody 1.5 meters tall of the same BMI, right? So basically, one has got a lot more cells to feed. But the thing is that, we do not have the capacity to go, looking at my plate, this is about how much I need to eat off that plate as a person who's 1.5 meters tall versus 1.8 meters tall. Another one, so basically it's the concept of health information, right? One of the things we ask is, do you know how many calories there are in a glass of water? And if you don't know, the probability of being obese is 27% almost there. And if you do know, it's 17%. Once again, it's a bit like educational status, but just a bit more impactful from the point of view of, well, we can't just go around thinking, hey, if I tell everybody, hey, there's no calories in a glass of water, and suddenly we'll make the things better. But on the other hand, it's predictive, right? So once again, it's the big difference between being predictive in a correlational sense versus predictive in a causal sense, right? So that's just 1, 2, 3, 4, 5, 6 examples from something where we have literally hundreds and thousands of variables, not 6, right? But once again, each one of those in itself just poses many other questions about what the hell is going on. Why is height so related to that? What's happening as a function of age, etc. Right? So the question is, well, what are these effects direct or indirect? But why the conductome is because essentially the principal intermediary between the effect and the causes is your conduct, what you do, right? And that's why it's of enormous interest to us. So I'm not going to go into much depth about what the hell is a behavior, right? So the Dictionary of the American Psychological Association says it's an organism's activities in response to external or internal stimuli, including objectively observable activities, introspectively observable activities, and non-conscious processes, right? Okay, and this is where, with my physicist hat, turn that into something quantitative, right? So the thing is, well, what the hell is an introspectively observable activity? What, how do you measure them, et cetera, right? And to me, the way I try to look at it is that, okay, well, just as in any physical system, an organism has a particular state. Well, okay, what particular changes of state can be identified? How do I identify a state? Well, I need state variables, just like any physical system. And then I can look at the changes in those state variables and say, okay, well, what changes in state variables can I associated with intuitively a behavior versus not, right? Once again, there's no time to go into that in much more depth. But one thing I did want to emphasize that's important is characterizing conduct as a statistical inference problem, right? So, there's no notion of going, hey, there's one event that you look at and you go, that's a behavior, right? And often we won't think like that. So in other words, in our own mental models, we have an intuition. In that sense, we have our own, when I talk about a mental model, basically we have prediction models inside our own heads that are associated with, let's call them statistical ensembles, except they're not ensembles in a standard frequentist sense. They're basically ensembles, let's call them, of a more Bayesian nature, where we have beliefs about everything, right? But independently of whether, let's call it, it's an external, I'm going to call it an external ensemble, where you have a behavior and we're going to say, hey, this person did this, and they did this, and they did this, and we count how many times they did it. And then we try to construct probabilities, et cetera, et cetera. Basically, that's what we do, but internally. But once again, we don't do it, basically by infrequentist means. I mean, it's basically impossible to do it that way. So there's a huge difference between how we make a statistical inference as scientists, where we try to do a controlled experiment, and then we do counting, let's call it, versus how you have to do these inferences in your daily life, where you have heuristics in the brain, let's call it, that are estimating plausibilities, right, from a Bayesian sense. And then it's a question of how is one related to the other. And one of the main things we try to do is to say, okay, let's try and compare what this person's internal model is doing versus what happens in reality. To give an example, one person might be saying, oh yeah, I do go to the gym, and that's their belief. But the thing is that if you follow them for 6 months and you go, well, you don't actually go to the gym anywhere near as much as you pretend you think you are, right? So in other words, what we would claim is that there's a huge, one of the main reasons why, there are many important social problems is basically the divergence between our internal models and what data will actually tell us. I'll give a couple of examples of that. So what are the hypotheses behind the conductome that human conduct or behavior can be predicted and explained probabilistically, both transversely and longitudinally? Also that we can do it with a Bayesian probability. So once again, that P of C of X is everything, right? That's what I want to calculate. It's what we calculate with the heuristics in our head for our internal models, where X are the, let's call them explainers or predictors, and it's this idea of X being exceedingly multifactorial. But the multifactorial, besides having some consequences that are methodological, it's also a huge challenge from the point of view of, once again, how do you get data sets or generates data sets that are capable of covering the set of explainers that are relevant for a phenomena like obesity, right? That there's an internal conductome that is constructed by any organism and every organism. And then the claim after that is that, well, by far the most appropriate models, and this is where I diverge from, let's call it, being a physicist with a little 2, 3, 4 variable model, where basically you need to be talking about sophisticated statistical models, machine learning models, etc., that account for that multi-factoriality, right? And then those are some caveats to how you go about basically analyzing those hypotheses, right? There's no real good quantitative definition of a conduct or behavior. We don't have a good taxonomy. We don't, for me, one of the things I try to say that distinguishes our work is that this idea, who has data sets that cover the gamut of explainers, let's call them, from the genetic to the sociological and socioeconomic, et cetera, right? And then even if you do have that a larger set of factors, what the hell are the relations, causal and non-causal, between them? Why the hell is it that people who don't know how many calories there are in a glass of water have a higher obesity rate than those who do, right? One of the nice paradigms, and this comes from evolution algorithms, where I did a lot of work for a long time. It's the idea of a fitness landscape, right? So it's a very powerful paradigm, and what I like to think of is a probabilistic one that's representative of, let's call it a conductome, right? So in other words, if you think of having a height function that is this probability of a particular, say, behavior as a function of these factors, well, you have a base space that's all those factors. And the point would be is that, the mountain peaks mean you've got a high propensity for that behavior, and the valleys mean you've got a very low propensity relative to some baseline, right? And you can take the baseline as just being P of C without any x's at all, right? And so you can think of that almost like a decision or an action threshold. Above that, you're more likely than random to basically exhibit the behavior, or less, right? And so the thing is that what we're trying to do is to basically construct this, let's call them conductome landscape, as opposed to a fitness landscape. And from an important point of view of behavior change, what we're trying to do is to locate who is associated with the mountain peaks, and what degree of plasticity is there in terms of behavior change to move them from a mountain peak further down, right? So in other words, here's a particular, so imagine you could think about the higher education, the less likely you are to exhibit this adverse behavior, or the more cognitive stress, the more likely you are to exhibit this behavior. Well, okay, let's reduce cognitive stress as much as we can, and let's try and get people more educated. Obviously, one of the important things is what factors are more directly actionable in a short and in a short term, right? But one of the key things there is that there's not much point in trying to induce behavior change if you have a factor in a factor that's not very plastic at all, right? So that's one of the important things there. What is the degree of plasticity of a particular factor? So the thing is that, first of all, to try and implement this conductome picture, we need data, right? And so these are the phases that we've gone through with our work since 2014, the different populations that we have, et cetera, And one thing I've emphasized to Kate and Stefano is that the one thing I would like to leave as a legacy is basically the data, right? And this is a huge challenge just in and of itself for anybody who works with large data sets or generated large data sets rather than working with them. Just the thing of cleaning the damn data, getting it nice and organized, et cetera, is a continuous and huge challenge, right? But the one thing I want to emphasize is that all of this data is publicly available, right? Meaning, hey, not necessarily publicly available in the sense of here's this website, it's been absolutely cleaned to the nth degree, 100% confident that it's trustable, et cetera. There's some that are much more cleaned than others, but the thing is that it's almost like generating data is easier than actually cleaning it after you've generated it, et cetera. But the thing is that this is the resource that we use for trying to basically generate these conductomes. And then the second thing is that what's the methodological approach to trying to put that data together to construct quantitatively a particular conductome, right? And we'll see a couple of examples. And I won't go into much depth here, but it's actually very simple, right? So first of all, we use a Bayesian approach, right? Meaning, okay, well, I want to construct these niches, right? I want to construct these conditional probabilities. So we use Bayes' theorem to basically relate that to a likelihood function. That's that P of X given C. And in some sense, the beauty of the Bayesian approach is to say, okay, here's my guess. It's called P of C, right? And for where my belief that who's going to be in this particular class, who's going to do, exhibit this behavior, et cetera, and then X is experimental data evidence that you will generate, and then you use that to update to a new posterior your idea of how likely it is that this particular person with now this data X associated is now going to exhibit the behavior. And then this can continue. P of C given X can now be a new prior where you just throw in more information. Now I have studied them for 2 more years. I've got now psychological data as we do, et cetera, and now I'm going to update again. And you can just go continuously in time as well. As you discover more information about a person over time, you can just go from prior to posterior, from posterior being new prior, et cetera, right? Continuously adjusting and adapting your expectations about what the probability is for, say this particular behavior, or it could be a state, right? What's the probability of somebody have been obese? Now, the thing is that, why a frequentist point of view is useless when you're highly multifactorial. You can't just look at that PC of X and go, okay, it's the number of events where I see C and X together divided by the number of events where I see X. Well, if X is 500 variables, then the point would be is that the number of people in your studies, or even worldwide, that have a particular configuration of those 500 variables is either 0 or 1, right? It's almost like using as a factor your fingerprint. Well, okay, you can't do a statistical analysis on that because everybody's fingerprint is different, right? So how do you go about constructing that probability function? Well, that's where the different, let's call them machine learning algorithms come in, or whatever you want to. But the simplest is just this thing of using assuming factorization of that likelihood function, and basically saying that the explainers or the predictors X are independent one of the other. And then what you can find is that, okay, then I just have essentially a particular contribution there, that SI, that comes from one particular variable. Now, the thing is that, that's the most simplistic way of looking at it. You can combine variables. There's many things you can do, and people will say, obviously there's correlations between my variables, and I won't go into, okay, but the point would be is that those correlations can cancel. There's many things of why this approximation, even though it should not work, actually works very well. And at any rate, you can go beyond that approximation, etc. But it has a lot of things going for it, meaning, hey, everything's just counting now. It's incredibly efficient computationally. And the other thing is it's incredibly transparent. You can now manifestly see what the contribution is from a particular variable to my overall probability, right? Okay, so that's the method. So we have the data part, we have the methodological part, so you can put it all together, right? So these are the top 10, 15 or something most predictive factors for looking at a behavior. Well, what's the behavior? People who don't exercise on weekdays, right? So this is looking at from one of the populations, 292 academic and non-academic workers that were a follow-up study in 2019 from our first study in 2014, right? This is just one subpart of one part of that study. So in other words, we basically wanted to go into, so how would I divide up my factors that explain this? Well, I can divide them by discipline. These are the psychological factors, these are sociological factors, these are the etc., right? But to me, from let's call it thinking of a causal process point of view, well, okay, you can't get fat unless you eat more than you need, right? You know, as a physicist, well, the energy balance does play a hugely important role. So how do you end up eating more than you should? Well, first of all, you've got to have encounters with food. And then second, you have to take a certain decision in that encounter. So if I thought back to the thing about academics versus non-academics, well, you know, why do non-academics and academics have different either environments? So one has more encounters than the other, or they have the same encounters and just one makes a smarter decision, let's call it, and doesn't eat the fast food or whatever it would be. So the thing is that what we've got here is, and once again, this is what the general methodology does, is go, okay, factor number one, okay, what was the most predictive of people not doing exercise on weekdays? Well, people who have to look after the kids, right? So in other words, that's telling you, you know, 41% of people in the study weren't exercising midweek, but the percentage of people who do not exercise midweek, but hey, they have to look after the kids, is 71%, right? So, and that's very statistically significant. You know, how regular is your bedtime schedule? So that's fairly easy to intuit, right? How regular is your bedtime schedule? That's even more predictive, 82% of people, if their bedtime schedule is not particularly regular, right? You know, it's like 1 or 2 hours difference going to bed every night, right? Do you exercise on the weekends? Well, there's nothing to say that if somebody doesn't exercise midweek, they can't exercise hard at the weekend. But once again, there's a strong correlation there because habits are habits, right? So once again, this is just a very small subset that's associated with a particular questionnaire that we tried to basically find out what was somebody's day like from the moment they wake up to the moment they go to bed, and then to go, okay, I'll use that to try and look at somebody's environment. You know, how often do they find that they fast food places? Once again, you know, there's hundreds and hundreds of variables there, and what I'm just showing there is the like top 12 or 15 or whatever. But you know, in some sense, you know, here's another one where I'm showing much more the psychological aspects, right? So this is one we're doing just in the last couple of years to a bunch of undergraduate students from private and public Mexican universities, and behavior is very similar to do with exercise, but it's exercising more than 2.5 hours weekly. And once again, you can go through this and go, okay, now, so we're working with a bunch of psychologists from the psychology faculty here, and, you know, okay, well, here's a questionnaire for locus of control, here's a questionnaire for self-efficacy, here's another one for anxiousness or depression and things like that. So the thing is that we can throw them all in the box, right? You know, the box is P of C given X, and then we go, what comes out? Well, you know, what comes out is an ROC curve where you can go, okay, I just throw it in. Now, how well can I predict who's not doing exercise, right? And the point would be is you can predict very well, right? The challenge then is to go, okay, well, it would have been great if I could have predicted it really well with just 2 factors, but no, right? You basically need many, 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 many factors. And then the question is, what the hell do I do with that, right? So if I'd had 10 or 12 hours, or we had an hour seminar for the next 6 months, I could go through factor by factor, type of factor by type of factor. Here's PowerPoint number 1 with this factor, height. Here's PowerPoint number 2 with et cetera, and you can have very interesting discussions about every individual factor plays a role, right? But unfortunately, that's not how we do science, right? Meaning, nobody's going to sit through the hours and hours and hours of trying to go through every single factor. But for me, just about the most important lesson to learn is that it is incredibly multifactorial in that sense. You can't ignore the fact, that there's factors from the psychological, there's factors from the genetic, there's factors from the environment, there's factors, right? And what the hell? So first of all, the most important thing is to at least accept the fact that there are many different factors. And once you accept that, then at least you can start posing the questions about, well, how do they relate one to the other? But one thing to think about is, we came up within a year or just after to get a vaccine for COVID, right? Simple problem, right? It sounds terrible to say it's a simple problem. How well have we done in persuade people to get vaccinated? In places like the US, et cetera, that's a much harder problem, right? So these questions of the conductome and basically how do you change people's behavior, a lot more difficult problem than coming up with vaccines and things like that. And we've been investing tremendous amounts of money in trying to reduce the obesity epidemic worldwide for decades now without much success, right? So we should pose the questions to ourselves as scientists, doctors, et cetera, why is that, right? And so this is my, let's call them answer as to why it is so difficult, because it is so incredibly multifactorial, right? I won't go into unless there's time at the end to go a bit more into some individual factors. What I wanted to basically end with is the following, right? So so my goal with this is to say I can construct this P of C given X from data, right? I can construct what's the probability of somebody exhibiting this behavior or exhibiting this particular physiological state, et cetera. So the point would be is that is a prediction model, and it's a prediction model, as I emphasized, that comes from, let's call it an external ensemble, right? I'm trying to be a scientist. The thing is, I'm not doing controlled experiments, right? In that sense, I'm just trying to go out to the world, just gather data and then use that to try and construct these probabilities, right? It's the traditional scientific approach of divide and conquer is useless from this point of view. If I have 500 factors, basically what am I going to do? Experiment 1, I'll look at factor number 1 and try and control for the other 499. In my next experiment, I'll go to factor 2 and try and control the other 499. Forget it. It's just literally impossible, right? So the basically, science has to move on to just trying to have, let's call them naturally generated data. That's not just a question of a controlled experiment, right? But what I wanted to then do is to say, well, okay, we have these prediction models whereby, okay, we can represent the world in data and then try and determine what are the factors that influence a particular behavior, right? But from this point of view of what we are is a big set of prediction algorithms as an organism anyway, how do the prediction models get generated internally, right? So in other words, when we make a decision, what is the prediction model we're using to make that decision, right? And one of the ones I like to think about, you walk into a building or your own work or something like that, there's an elevator and the stairs. what are the factors that go into basically deciding whether in a given situation you're going to take the stairs versus you're going to take the elevator, right? What's going on inside your head, right? So basically, from the external ensemble point of view, what we could do is just, okay, here's a big population of people. I'm just looking at them, saying who takes the elevator, who takes the stairs, and then I'm going to ask them all sorts of things, take blood sample, do whatever you want, and then just try and construct that external ensemble to find, okay, what's the probability of somebody taking the stairs given that of this state, right? In other words, call it a subject state there and the environment state, right? Meaning, hey, okay, it could be a case of, if there are many stairs, few stairs, if the elevator is slow, if there's a lot of people waiting for the elevator, if your friend is already waiting for the elevator, okay. So the point would be is that we can look at it from an external ensemble point of view, but in some sense that doesn't tell us why somebody makes the decision to do one or the other, right? So why does someone take an escalator versus or a elevator versus the stairs, right? It's the idea of when is the decision, let's call it good versus bad, right? So we need a metric to measure it. Basically, that metric has been kind of given to us from rational decision theory, basically saying that what humans are, we just utility maximizers, right? There exists some function that we don't have in hand whereby I make my decision to maximize that function. But I think one of the huge disadvantages of that perspective is that there's no one function that we want to basically optimize. There are many, right? So in other words, you'd like to get from one place to another as quick as possible. On the other hand, you'd like to get from one place to another without having to exercise so much energy, so that you're exhausted getting from one place to another. You'd like to get from one place to another, not investing so much energy, but getting a good health benefit. So in other words, there are many different, let's call them utility functions that we need to balance as trade-offs in our decision. And from a physicist point of view, what this is, it's a frustrated system, right? Meaning, hey, you can't satisfy the desire to get from A to B, say, quickly. Like you can't take the elevator and think, hey, I'm getting a good health benefit from that at the same time, right? So the point would be is that many of these objective functions are, let's call them mutually exclusive, right? So the idea behind this, and once again, this is pure theory, right? I mean, it's just, how do I think I might get inside somebody's head to think about how would we make decisions. So if I take a particular decision and a particular action, so basically the claim is that I have these different value functions, right? Meaning, let's call them different utility functions. I want to be able to reduce the time, not expend so much energy, etc., etc. And then the point would be is I can define a decision as being a good or bad with respect to any one of those, right? So in other words, I didn't expend so much energy, etc., etc. I got there quick, etc. But once again, these different value functions are not mutually optimizable, right? So in other words, it's a frustrated system. Now, the thing is that you could, in principle, try to find out whether somebody actually had a gain or not in one of these value functions post the action, right? But what the claim is here is that there's what an organism does, or what humans certainly do, is, let's call it, there's a pre-action evaluation, right? So in other words, when you are faced with a decision, basically what you're doing is trying to estimate, predict what is my payoff going to be for each one of these value functions. And then your final decision is essentially coming in from that. And then this is the last slide. So basically, what the claim here is that our internal heuristics are basically what I would call a meta prediction model, right? So in other words, your prediction or your decision is not just a function of data, it's a function of other prediction models, right? So in other words, you're predicting how much a benefit I'll get from an energy point of view, from a time point of view, from a socialization point of view, from a health benefit point of view. And then those are the things, those prediction model outputs go in as inputs for a new prediction model, which is saying, okay, given those estimated payoffs, what's my decision now? I'm taking the elevator, right? And obviously that depends on your state, whether you're tired, whether you're et cetera, right? So anyway, to conclude, basically all major human problems are consequences of human conduct. Decision-making and behavior immensely multifactorial. Data-centric omic approaches have revolutionized microbiology. Such approaches can and should be applied to human conduct, although human conduct is a lot more multifactorial, multi-scale, and multidisciplinary than any phenomena that ever exists in microbiology. The conductome, I would claim, is a conceptual and theoretical framework within which data-centric external ensemble, in other words, just getting the data and saying, I'm going to try and construct these niche models, can and have been constructed, So I gave a couple of simple examples with just a few variables there. But it's a huge challenge to understand what the hell these models are telling us, right? So you can just throw your hands up in the air and go, well, I don't care. But the point would be is that the proof is in the pudding. Is one nice thing about say machine learning, predictive modeling from the point of view, well, let's call it feature selection. If you can put in 2 more variables and you get better predictability, then that's telling you those 2 variables have got something in them that your previous variables didn't have, and you need to understand it, right? So the point is, if you throw in more and more variables and you don't get any benefit, let's call it from a predictive point of view, then, they're not predictive per se, right? You can forget about them from that point of view with that particular conductome. So there is a way of quantifying and basically analyzing whether you get a predictive benefit from putting in this variable versus this variable versus this variable, right? So you can go, hey, who cares about psychology? I put those psychological variables in and they don't help me predict who's going to do exercise or not. Well, no, they do predict. But so does, whether somebody has to look after the kids is also predictive, or whether somebody, etc., right? So it's an even bigger challenge to understand this concept of an internal ensemble, and it is that in reality governs our behavior, right? So, once again, the hypothesis of the human decision-making is a meta model where the final the decision depends on the predicted payoffs from multiple prediction models, one for each objective. I don't have, let's call them experimental protocols that go delving in on that. In that sense, it's just a theoretical idea at the minute, but the external ensemble ones, well, all the data is there ready for everybody to look at if they want to, and to use their favorite algorithm to start generating predictions or just looking at a subset of data, et cetera, right? So once again, we have 7,500 participants about now and thousands of variables from the micro to the macro. I've emphasized to Kate and to Stefano, we're drowning in data, right? The final thing is all this work has been in collaboration with a very large interdisciplinary team. I'm completely dependent on them, and you can find more information at our site Chilam about the conductome and the other projects that we have in that direction, and I'll leave it there.
Thank you very much. This detailed talk. So I now ask if there are questions. So I have a question while the others think about it. So of course, you have so many variables, no? You said 1,001, but are they all, let's say, independent? Probably not, no? Some variable maybe. So can you somehow cluster these variables and put them into boxes, and they more or less be the same? Not like, I don't know, people who I don't know, who exercise do also something else most of the time, and so on. So that there are conducts that are sort of correlated. No?
Yeah, I mean,
so instead of having 1,000, can you reduce it? So what is the minimum you can reduce without losing? Because of course, if you have 1,000 variables, then there is no hope. No, if you want to keep all of them, of course, at least it's very hard. No. But if you can cluster into groups, maybe it's easier to understand, and that can give us some guidelines.
Well, the difference there, Stefano, is it's the antagonism, let's call it, between predictability and explainability, right? The thing is that one of the things as scientists, we think that explainability comes about from few variables. And that, I would claim that that's more of a comment on the limitations of the human brain rather than the phenomena themselves, right? Obviously, as physicists, we're very honed to that, right? Nice, simple theories theories of the physical world should be nice and simple, right? And I think for complex systems, that's clearly not the case. But what I was trying to point out there, with respect to your question there, is there's a direct route to going clustering or not, right? So in other words, if you have a box, right? So when I mean a box, it's like, let me just show this quick. Can you see that? So this is an Excel with the 2049 variables that I've got for one of these conductomes, right? Now, the point would be is that it probably isn't so easy to see. So the thing is that with all the psychologists we work with, there'll be an instrument. There's a box called locus of control, right? Do you think you control the world? Do you think the world controls you, right? Do you have an external or internal locus of control? There's gratification delay, right? There is self-efficacy, right? There is, so in other words, every one of those is a box, right? A psychologist is going to go, hey, no, forget about these individual things. I got this box, and it's called impulsivity. I got this other box that it's called locus of control. Those are the boxes that are important, right? So in that sense, what they'll do is you go, okay, here's 20 questions in the box for locus of control, but no. The only thing that's important is my total score on this scale, right? Effective degree of freedom, let's call it. And then what we do is we go in and we go, okay, what's more important, the box or the things inside the box, right? And so what all our methodology is allows you precisely to go and say box versus sub box versus the sub box, which is the actual individual question, right? And then the question is, well, okay, if I find that the individual questions are more predictive than the boxes, well, what do the boxes help me? Explainability, etc., etc. What do you want? A theory that's less predictive, but well, at least I can understand it, versus something that's very predictive, and then it's up to you to find, well, what the hell do I need to do to understand it, right? One of the things here, so the thing is that if I go down, this is listed by their degree of predictability. The one thing that comes up is one of my one of the grad students working in a problem, working in this, was when, hey, what I'm going to do is I'm going to make a box, a new box. What's the new box? It's any question that had the word food in it, right? Or eating or something like that. And you find that that's actually looks like a much better box than locus of control or gratification delay or etc. Right? So the point would be is that But that doesn't mean that it's, okay, I just use that box. Because the other thing is that what's key is, let's call it actionability, right? So in other words, what I challenge all my psychologist friends, okay, here you score high on the locus of control box for whether you're going to do exercise or eat properly or et cetera, et cetera. Okay, do I, in that sense, the questionnaire itself is let's call it a locus of control-ometer, like thermometer or et cetera, right? Now, can I go to a person and go, okay, now I've got thinking that landscape, conduct on landscape, now I've got this intervention that makes you go lower on the locus of control scale or higher on the locus of control scale, right? Versus the semantics of looking at the question and going, hey, part of that locus of control is, hey, I can't resist eating chocolates and sweets when I see them. Well, I can't resist eating chocolates and sweets when I see them is a lot more actionable than going, okay, you have a very external locus of control. I think you need to get your act together and get a more internal locus of control. Yeah. So in other words, you can look for boxes, but then we can say, does the box help me? Either it's more predictive, less predictive, versus more explainable, less explainable. And then the key is it actionable? Does that box allow me to go, I can get higher or lower scores on the box? But the key to me is, you ain't going to get 1,000 variables down to 2. I can guarantee that, right? But the way to tell me how many boxes I need is just say, hey, I put in another box, do I get more prediction? Another box, do I get more or less prediction, etc., and use that as the pragmatic approach, forgetting about explainability for the minute, right? Because explainability to me is, once again, a function of our imagination or lack of imagination in trying to understand the system. Yep. So it was a long-winded answer, but
thank you. There is Thierry who has a question, please.
Yes, actually, it's connected to your question. So I was wondering if there is maybe already enough information in the genetic variables you have, because ultimately I would expect that all the other are AP variables that are somehow connected to the genetic data and to the genetic variables. So somehow I would put forward the hypothesis that everything can be explained at that level. But actually, I'm not, of course, an expert about diabetes, so I'm not sure even if it makes sense what I'm saying. But somehow I would expect that if you work at that level, at the genetic level, you should come up with the same performances, the same accuracy in the classification and so on.
No, basically, I think the absolute opposite is true. And that's what the example I was trying to I didn't go into depth. I mean, we were only looking at those 300 SNPs, right? But the thing is that, our National Genomics Institute gets a lot of money from, well, it's the Broad Institute in Harvard gets a lot of money from Carlos Slim, who is was one of the richest men, well, still is one of the richest men in the world, right? And they'll spend millions of dollars and go, wow, we just found 15 more polymorphisms that are linked to diabetes. We don't necessarily know much about, what's the physiological connections going from the gene to the etc. I am absolutely convinced that for something like conduct, this reductionist approach of polymorphism by polymorphism is a complete waste of time. That's not to say it's a waste of time for many diseases, etc., right? But on the other hand, where I would agree is that our genome, completely not polymorphism by polymorphism, but the fact is that human beings and organisms in general have tendencies, right? And those tendencies are associated with our evolutionary past and therefore by definition associated with our genetics. The fact that academics and have a 13% obesity rate and workers 40% obesity rate, unless you're going to propose that the genetics of academics is completely different than the genetics of workers, which would sound a little bit eugenics like, then it's clear evidence that no, it's like genetics doesn't count that much from that point of view, right? Another famous example is the one of the Pima Indians in Arizona versus Chihuahua in Mexico, right? Where, basically same genetically, but the obesity rate and diabetes rate, the diabetes rate was 50-60% in Arizona, and until recently, very low in Chihuahua, right? So in other words, you can have a genetic susceptibility, but you need the environment, and more particularly your conduct in that environment is an absolutely necessary condition to detonate it, right? So yeah, I mean, I think, there's good evidence to say genes from the point of view of individual genes, in the sense of a polymorphic point of view, no, is completely the wrong way to go about it. But where I would agree is that we have tendencies in our behavior that are basal tendencies. So in other words, there's a basal tendency for both academics and workers, but there's things on top of that: culture, education, decision making, etc., knowledge that basically can adjust those tendencies, right? And it's the combination of the two that makes the thing highly complex, and how to basically disaggregate one thing from the other.
Thank you.
So I don't know if there are other questions. I think